When we watch a high-speed impact, human intuition perceives unpredictable chaos. Parts scatter, energy violently disperses, and the outcome feels random. But if we freeze the action at the exact microsecond of impact, a different reality emerges. Beneath this apparent chaos lies mathematical order. In physics, a collision is an event driven by mutual, impulsive forces acting over a microscopic time interval, denoted as delta t. To understand these forces, we use linear momentum. Linear momentum is the product of an object's mass and its velocity. There is a rule governing this system. In any collision, the total linear momentum is conserved, from the exact moment before the impact to the moment after. Because momentum is conserved, we possess the mathematical framework to calculate the exact trajectories of these objects before the dust even settles. Why is momentum conserved, regardless of whether the objects are billiard balls or freight trains? The answer traces directly back to Newton's third law of motion, which states that every action has an equal and opposite reaction. During an impact, the force the first object exerts on the second is exactly equal and opposite to the force the second exerts on the first. Both act over the exact same time window, delta t. Therefore, the resulting momentum changes perfectly cancel out. The formal mathematical result is that the total impulse on the isolated system is zero. Because the net impulse is zero, the total momentum remains unchanged throughout the impact, providing a reliable mathematical constant regardless of the objects involved. If momentum is always conserved, why do some objects bounce off each other while others crumple, shatter, or fuse together? We have to look at kinetic energy. Kinetic energy acts as the discriminator that determines the physical type of collision we are observing. This compressed spring model visualizes deformation during impact. In elastic collisions, the spring perfectly regains its shape, returning kinetic energy. In inelastic collisions, it permanently deforms, losing energy as heat. If completely inelastic, the bodies fuse, maximizing energy loss. Note a crucial caveat. Even in perfectly elastic collisions, kinetic energy is temporarily converted to potential energy during the microscopic duration of impact. For the fused inelastic scenario, the initial momentum equals the newly combined mass of both objects multiplied by their shared final velocity. While momentum dictates the axis of movement, kinetic energy determines the physical severity and the final state of the objects involved. Head-on collisions are straightforward, but most physical impacts involve glancing blows, like sinking a target ball in a corner pocket. This models two-dimensional impacts. Initially, all momentum is along the horizontal x-axis. After impact, the masses scatter diagonally. To apply conservation laws, we break these paths into orthogonal components, using cosine to calculate the x-axis horizontal momentum and sine for the y-axis vertical momentum. Notice that the y-axis equation equals 0. Because vertical momentum did not exist before the impact, the upward and downward post-impact momenta must cancel out. Solving these equations requires knowing at least one resulting angle, usually measured by a detector or determined by the geometry of a billiard table. Adding a spatial dimension does not require new physics. It simply requires geometry to enforce the exact same rule of momentum conservation across a plane. Does a collision actually require two objects to physically strike each other? To answer that, we pivot away from the macroscopic world of billiard balls and solid blocks, zooming down to the subatomic scale. This process is called scattering. An incoming high-speed alpha particle approaches a dense atomic nucleus. The mechanism here is intense electrostatic repulsion. The incoming alpha particle is deflected off its path before any physical contact is made. This action at a distance feels counterintuitive when compared to the everyday mechanical impacts we are used to seeing. Yet, despite the complete lack of physical contact, physicists classify this interaction mathematically as a perfect collision. While we perceive the audible crunch of an impact, the physical definition of a collision centers on the isolated exchange of forces between two bodies over a specific duration of time. We can prove the universality of the math by applying the exact same two-dimensional vector resolution to this invisible force field interaction. The alpha particle's scattering angle and momentum shift obey the identical sine and cosine equations we derived for the billiard balls. A wooden block, a billiard ball, and a quantum particle all bow to the exact same mathematical framework. From the orbital paths of comets to the interactions of subatomic particles, the conservation of momentum provides a consistent mathematical framework for predicting physical outcomes across every scale of magnitude.